Hi everyone, how you doing? And welcome to another science video with me, Clara, Dr. Clara Barker. Yes, so hi, thanks for coming back. And in this video, it's going to be a continuation of my talk about superconductors. And in the last video, I talked about the electrical properties of superconductors. In this one, I'm going to talk about the odd magnetic effects that we see with superconductors, the things that get a lot of the press. So without further ado, let's talk about it. All right, so we've got our superconductors once again, and this time, yep. See, I've got a video here. So this is a figure-of-8 track, and in this little polystyrene cup. So this is, I've got a superconductor glued to the bottom of it. This track is made of magnets, so there's an outer field. So it matches on either outside, on the two outsides, but there's a different field on the inside. So north on the outside and south on the inside, or vice versa. I don't really know, I've not checked. And in this polystyrene cup, we've got the superconductor and a little bit of liquid nitrogen to keep it cold. So we talked about superconductors in the last video. We said that they had to be cold in order to get the electrical properties. Well, the magnetic properties are the same. So what we've done in this is we've cooled down the superconductor and it's kind of floating, levitating above this magnetic track. And so we'll talk about how and why. Here we go, magnetic properties. So once again, in the previous video, we were looking at the atoms and they're all in this particular structure, and we were talking about the electrical properties. Here, we're talking more about the magnetic properties. So we've got this superconductor, this bulk, this collection of atoms, and we introduce a magnet, a magnetic field, in the nearby vicinity, and when the superconductors are warm, then the magnetic field passes through it. If it's a magnetic material, then it will induce a magnetic field. But you know, the magnetic field lines are passing through, so we know that they're going from A to B. So they're not traveling in a straight line up; they're actually moving round in a particular place to get to a south pole. But for this example, we're saying that they're traveling straight through. Now, if we take a superconductor, and with the superconductors, as we did before, we're cooling down the superconductor, right? We're actually cooling down the superconductor, and what we find is that rather than traveling through once they get below the critical temperature, the magnetic fields are expelled. The superconductor won't let these magnetic fields pass through the material. Basically, there's just no way. The magnetic field is, you know, or is sort of an invisible thing, this invisible force. It won't let it through the material. It just will not let it through the material. It has to go around. And so that's super interesting. And I should point out that this happens at the same temperature as the electrical properties kick in. So, you know, for the superconductors, once you start forming these Cooper pairs, then we also start to see this odd manipulation of magnetic fields around. And this example here is a type 1 superconductor. This is a traditional superconductor, a lot of metals and stuff. However, we also have type 2 superconductors, and it's even stranger. So now these magnetic field lines are passing through as the superconductors warm, but as it gets cold, what happens is that actually we start to pin the magnetic fields. So it's not excluding it. It's not. It allows them through. It's not forcing it to go around, but it's saying you can come through, but you can only come through in a particular place. You can only come through. Basically, it's acting like a gate, and so this is a flux pinning site, and so the magnetic flux can only travel through these pinning sites. Now there might be billions of these pinning sites, but the magnetic field can only travel through this field, this gate, basically. And so what we find is that we're almost sort of forming channels. You've got your magnetic field lines, and there's these tubes. It's like, this is where the field comes through. This is where you travel through. And so what happens is that if we've cooled down our superconductor and we've trapped these magnetic fields inside them, then when we move the superconductor and you've still got the magnet in place, what happens is you move the superconductor, and this is slightly exaggerated, but the magnet has to go with the superconductor. Basically, you move the superconductor and it drags the magnet with it. And the opposite is true. If we move the magnet, then the superconductor will get dragged with it. And so we've actually really pinned these two things in place. They are locked relative to each other. And so that's what we see with things like this. We've got this little video and we've got the magnets on the bottom. So there's the outer field and the inner field, and the top is the superconductor, and we cooled it down. It's trapped these fields, and so it bounces along. It's levitating above it. This is the levitating hoverboards, right? And it can travel vertically across it because the shape of magnetic field is even all the way along the length of it. So you've got a kind of M shape, and so the superconductor can travel along the length of it, but it can't move across it because it's locked in place. Now, of course, if you apply enough force, then you'll be able to remove the magnet or remove the superconductor. You'll be able to move them from each other, but then if you put them back close to each other, they'll actually lock back in place. They'll kind of snap too. And it is a lock-in. It is a relative lock-in. If we go on and look at this is actually a superconductor inside a cup of liquid nitrogen, and below it is a magnet. And so we've done it the opposite way. We're actually suspending. So there's no wires or anything. That is just floating below the superconductor. It's locked in place. The relative positions are locked. Now, I should say that with these type 2 superconductors, if you cool them down and there's no magnetic field near the superconductor, then it acts like a type 1. It won't allow magnetic fields to pass through. It won't trap any fields because there's no field to trap. But if we do cool it down in the presence of a magnet, then we get this happening. And so this is really cool. You can suspend these superconductors or you can float them on top. And in fact, if we come back to our example, if we rotate, say, the superconductor or the magnet, then it'll go with it. So hopefully in this experiment, and so here we've got the magnetic track again. We've cut down the superconductor. It does warm up quick, so I have to be quick. But you saw that it was floating above the magnetic track, and then I turned the magnetic track upside down, and the superconductor went with it. So it's floating on top of it, and then I flip it upside down, and it's now suspended below it. So the relative position of the superconductor to the magnetic field stays constant. And so yeah, I think that's kind of cool, right? I think that's pretty cool. So that's our superconductors. So we've talked about the magnetic properties and how it reacts with external magnetic fields, and we talked about the electrical properties. So magnetic fields, I think, are easier to visualize because you can actually see them, right? Whereas it's a little bit harder to show that we've not got resistance in a practical demonstration, which is why you always see the magnetic properties being displayed. But there's so many things that we can do with this. It's great if you've got superconducting bearings. So you've got the magnetic race and the superconductor bearing, and it's going to travel around, and it's there's no resistance there, right? It's not in contact. And magnetic levitation trains. Now, there's different ways that the magnetic levitation tracks work. Some of them use superconductors, and it's a little bit more complicated than just doing what we've done there. They actually magnetic levitation trains pulse. They have electromagnets rather than magnets, so we turn the magnetic field on and off. But again, you've still got this cool stuff happening where you've got superconductors and you've got basically levitating trains. So we do have then. That's really cool. It's just, as usual with the electrical properties, you know, you've got to cool it down. It's got to be cold. You need liquid nitrogen or liquid helium to cool it down. So not quite there for you, making our hoverboards yet using this technology, but who knows? Who knows what's going to happen in the future? So with that, thanks so much for watching once again. Feel free to like and subscribe, I guess. And with that, I'll see you again soon. I'm not sure what the next topic of my science talks is going to be, so I guess we'll find out together. Bye.